Hi, my name is Haris Jalani, and this is my fourth lab for Physics 2211. In this lab, we will discuss the motion of an oscillating object. The objective of this lab is to analyze the energy transfer and motion of a spring mass system where the mass is oscillating on a string while swinging in an arc, essentially having both horizontal and vertical motion. The fundamental principles that I will use to analyze this are Newton's second law and the energy principle. To give an overview of what I did, I analyzed the motion of the given video using Tracker. I then constructed a model in GlowScript to predict the motion of the spring mass system, and finally, I compared the predicted and observed motion in a graph, or multiple graphs. The results I found were there were slight discrepancies between the Tracker and GlowScript simulation, but they ultimately had very similar graphs. I was able to compute the spring constant of 6.87 newtons per meter, the period of oscillation, which was about 1.52 seconds, and the relaxed string length, which was about 0.127 meters. Here you can see the fundamental principles and equations that I used in this lab to calculate the values needed to complete the simulation. The majority of these pertain to the forces used within this lab, specifically the calculation of the kinetic, potential, and spring potential energies, and the changes of these energies. You can also see Newton's second law, where force is equal to mass times acceleration, as well as the velocity update formula and the energy principle, where the change in energy is equal to the work done on or by the system, which is equal to the sum of the change in kinetic, potential, and spring potential energies. In this lab, the system that I chose was the Earth, the mass, and the spring, so there should not be a change in total energy because no work is being done on the system. Here you can see the Tracker simulation and data. Here you can see the calculations that I did to find the unknown values needed for the GlowScript code. We were given in edX video 52 that the mass of the object was 0.402 kilograms and the stretched length of the spring was 0.7 meters. We know the formula for the period of oscillation, which is equivalent to 2 pi times the square root of the mass over the spring constant. Plugging in these values, we find that the spring constant is approximately 6.87 newtons per meter. We also know the spring is initially in static equilibrium, meaning that the magnitude of the force of gravity is equivalent to the magnitude of the spring force. Plugging in our known values again, we find that the relaxed length of the spring is about 0.127 meters. Knowing these values, we can now plug these into the GlowScript code to finish our simulation. To the top left, you will see the system properties and initial conditions. We already know the object's mass, and through Tracker, we find its initial position. We know its initial velocity is 0 because it starts at rest. To the bottom left, you will see further values which affect the simulation. We know gravity is equal to 9.8 meters per second squared, and we've already calculated the spring constant and relaxed length of the spring. Below, you see 3 lines defining the vector L, which describes the orientation and length of the spring. We will need this to calculate the spring force, as well as the spring potential energy. Finally, at the bottom, you can see 4 lines defining the 3 types of forces based on our equations from earlier, as well as the total force, which is the sum of these 3 forces. To the right, you can see the loop of code which actually defines the motion and creates the graph. We first define our initial energies, as well as gravity and the spring force, based on the directions they point and the directions of motion they affect. We then say that F net is equal to F grav plus F spring because in this simulation we are only accounting for the effects of the spring and gravitational force. We then apply our velocity and position update formulas, as well as update the position of the spring. Finally, we calculate the energy changes using our predefined formulas to calculate changes in kinetic, potential, and spring potential energies. Here you can see the graphs created by the GlowScript code. As you can see, they're not a perfect match, but the Tracker observed motion is very similar to the GlowScript predicted motion, with some slight discrepancies which can likely be attributed to human error or other forces acting on the system. To the bottom right, you can see the energy versus time graph. The yellow line, which represents delta E, lies along the x-axis, which is exactly what we want because we don't want any work on our system. In this model, the energy principle was satisfied because there was no change in total energy. Because we set the system as Earth, the mass, and the spring, there was no work done on the system or by the system. This is corroborated by the graph where delta E is equal to 0. There were changes in the individual energy types as energy was exchanged between spring potential, gravitational potential, and kinetic energy, but overall energy was conserved. Using the Tracker motion data, we were able to construct the period of oscillation for the object in spring. From the x position data, we find this period of oscillation to be 1.55 seconds, while the y position data shows that it was 1.52 seconds. These estimates are very similar, with the x position data being slightly larger. This makes sense because there are more forces acting in the y component, including the gravitational force, which is affecting the motion and causing greater acceleration. So overall, in this lab, we are able to analyze the motion and energy transfer of a spring and mass which are oscillating and have both horizontal and vertical motion. The predicted and observed values are very similar. Differences can be attributed to human error, such as imperfectly measuring the center of mass on the tracker motion analysis, as well as other forces such as air resistance acting on the object. We can see that the energy principle was followed because there was no change in energy, corroborating the fact that no work was done on or by the system. We can apply this lab to many real-life scenarios where an object is oscillating or undergoing many different types of motion and has energy transfers between these types but no net energy transfer.